Welcome to this lecture on organic chemistry. Today, we are going to explore a fascinating and highly useful reaction called oxymercuration-demercuration. Imagine you are trying to park a large truck in a crowded parking lot. If you just drive in recklessly, the cars might panic and rearrange themselves, causing a massive mess. This reaction is like hiring a professional valet to handle the situation perfectly. Let us dive in and see how it works. Now that we have our valet parking analogy in mind, let us look at what this means in chemistry. Oxymercuration-demercuration is a highly reliable two-step laboratory procedure used to convert an alkene into an alcohol. Why does this matter? Because normally adding water to a double bond can create unstable intermediates that shift around, changing the fundamental structure of your molecule. This method completely avoids that chaos. It adds water across the double bond, strictly following Markovnikov's rule, meaning the hydroxyl group attaches to the more crowded carbon, all while keeping the original carbon skeleton perfectly intact. Building on that foundation, let us examine the first step, known as oxymercuration. When the alkene comes near the mercuric acetate, the electron-rich double bond reaches out and grabs the mercury atom. Instead of forming a standard, unstable positive carbon that tends to shift around, the mercury atom forms a three-membered ring with the two carbon atoms. This is called a cyclic mercurinium ion. This ring acts exactly like a professional valet, locking the carbon atoms in place so they cannot rearrange. Because the mercury blocks one side, the water molecule must attack from the back, leading to what we call anti-addition. Now that we understand the mechanism conceptually, let us look at the chemical equation for this first step. The formula shows our starting alkene reacting with mercuric acetate and water. The symbol R represents any generic carbon chain attached to the double bond. HgOAC2 stands for mercuric acetate, which provides the mercury atom. As the reaction proceeds, the double bond breaks. The OH group from water attaches to the middle carbon, which is the more substituted one. The mercury group attaches to the end carbon, leaving a molecule of acetic acid as a byproduct. To make this even clearer, let us visualize the exact mechanism we just discussed. On the left, you see the alkene reacting with mercuric acetate. Notice how the mercury atom bridges across the two carbons, forming that rigid, three-membered cyclic mercurinium ion in the center. This is the crucial clamp that prevents any skeletal rearrangement. Because this bulky mercury group is blocking the top face, the incoming water molecule is forced to attack from the bottom, opposite side. This backside attack breaks the ring open, placing the hydroxyl group and the mercury group on opposite sides of the newly formed single bond. With the water successfully attached, we face a new problem. We still have a heavy, toxic mercury atom stuck to our molecule, which is unwanted in our final alcohol. This brings us to the second step, called demercuration. To remove the mercury, we introduce a chemical called sodium borohydride. This acts as a reducing agent, meaning its job is to donate hydrogen atoms. It attacks the carbon-mercury bond, breaks it completely, and replaces the entire mercury group with a simple hydrogen atom. The mercury metal simply falls away, leaving us with a pure, stable alcohol. Let us see the mathematical representation of this final transformation. Here, the intermediate organomercury molecule from our first step reacts with NaBH4, which is sodium borohydride. The arrow shows the final transformation into the finished alcohol. Notice how the mercury acetate group on the right side of the molecule has been completely replaced by a hydrogen atom, turning that end group into a standard methyl group. The symbol Hg represents the pure liquid mercury metal that drops out of the solution. Because we avoided unstable positive carbons, the carbon skeleton R remains exactly the same. Before we move on, let us see this with a concrete example. We are asked to predict the final product when propene reacts with mercuric acetate and water, followed by sodium borohydride. Propene is a 3-carbon chain with a double bond at the end. In this first step, we apply Markovnikov's rule. The hydroxyl group attaches to the middle carbon because it has more carbon neighbors, making it the more stable spot for the attack. Meanwhile, the bulky mercury group attaches to the less crowded end carbon. This sets the stage perfectly for the final removal of the mercury atom. Continuing with our propene example, we now move to the final step. We take the intermediate we just formed and treat it with sodium borohydride. As we learned, this reducing agent replaces the mercury group on the end carbon with a simple hydrogen atom. The result is a perfectly clean addition of water without any unexpected changes to the original 3-carbon chain. The final product is 2-propanol, commonly known as isopropyl alcohol or rubbing alcohol. We have successfully hydrated the alkene exactly where we wanted to, proving the reliability of this 2-step method. Now that we have successfully hydrated a simple molecule like propene, you might wonder why we go through the trouble of using toxic mercury. The true power of this reaction shines when dealing with bulky, complex molecules. If we used standard acid and water to hydrate a bulky alkene, a free carbocation would form. The molecule would instantly shift its carbon skeleton to stabilize that positive charge, giving us a completely different product than we intended. Oxymercuration-Demercuration prevents this shifting entirely, acting as a precision tool that guarantees the hydroxyl group goes exactly where we want it. Let us see this precision in action with a much bulkier molecule, 3,3-dimethyl-1-butene. Our goal is to determine the product of its oxymercuration-demercuration. One side of the double bond is attached to a carbon bonded to 3 other methyl groups. In the first step, the bulky alkene reacts with mercuric acetate and water. The cyclic mercurinium ion forms and acts like a clamp, locking the structure in place so none of those methyl groups can migrate. The water molecule then safely attacks the middle carbon, placing the hydroxyl group right next to the bulky tert-butyl group. Continuing with our bulky molecule, we proceed to the demercuration step. Sodium borohydride is introduced to remove the unwanted mercury group from the intermediate. It replaces the mercury with a hydrogen atom, yielding 3,3-dimethyl-2-butanol as the final pure product. If we had used simple acid and water, the major product would have been completely different due to a skeletal rearrangement. This example perfectly highlights why chemists rely on this specific reaction. It guarantees that the original carbon skeleton remains perfectly intact from start to finish, no matter how bulky or complex the starting material is. This brings us to an important question. Why does this matter in the real world? In pharmaceutical manufacturing and industrial chemistry, molecules are often incredibly complex and very expensive to build. If a chemist needs to turn a double bond into an alcohol to create a specific medicine, they absolutely cannot afford for the molecule to randomly rearrange itself into a different shape. A different shape means a different chemical, which would completely ruin the drug being synthesized. Despite the toxicity of mercury requiring careful disposal, the sheer reliability of this reaction makes it an indispensable tool. We have covered a lot of ground today, so let us summarize the most important ideas. Oxymercuration-Demercuration is a highly reliable 2-step method for converting alkenes into alcohols. Remember that it strictly follows Markovnikov's rule, always placing the hydroxyl group on the more substituted carbon atom. Most importantly, by forming that rigid cyclic mercurinium intermediate, it completely prevents any carbocation rearrangements. This ensures your original carbon skeleton remains perfectly intact from start to finish. You now understand both the mechanism and the immense value of this reaction in organic chemistry. Great job!